In the previous video, we looked at an overview of the lesson for probability topics and some important definitions. In this lesson, we'll do an overview of probability formulas. We'll look at the three main formulas: the conditional probability, the addition rule, and the multiplication rule. We'll get an overview of all three, then we'll get into some examples for conditional probability. And in the next video, we'll do the addition rule in more detail, and then another video for the multiplication rule. Conditional probability, P of B given A. This is read the probability of B given A. So that little line there is not a forward slash or a backslash. It's an up and down line that reads such that, or given that, or under the condition that, or under the assumption that. It means that A is assumed to be true, and it affects the probability of B, so that the probability of B is adjusted accordingly. We have a formula for it, which we'll go over in some examples. Then we have the addition rule, P of A or B. The addition rule is sometimes known as the OR rule because when we can phrase the compound event with the word OR, and it's the inclusive OR, meaning the probability of event A happening or event B happening or both in the same trial or as the single compound event. So this is the formula, which basically shows us that we need to add the probability of A plus the probability of B minus the probability of the intersection of the two events. And you may see that written A and B. And in this context, the A and B means that both events are able to be true at the same time in a single selection or a single trial or a single event. Okay, so both at the same time in a single trial. So we add the probabilities and, if needed, subtract off the overlapping probability. Now, it says if needed. That's because sometimes event A and event B are mutually exclusive, which means they cannot occur at the same time, making the probability of them occurring at the same time impossible or zero. Now, the multiplication rule is often known as the AND rule because when you can phrase something with the word and, it's usually something that can use the multiplication rule. But we have to be careful that we don't confuse the word and used here with the way that the word and is used here. The multiplication rule is for multiple trials. So this would mean A and then B. So that we're talking about the probability of A happening first and then B happening in a separate successive trial, one after another. So if this is the way that we can understand the problem, then we would multiply the two probabilities. But notice that the second probability is with that conditional probability notation that we saw up here. So what that means is that we assume A happened on the first trial, and now the probability of B may be different than it would normally be. And so if it is different, that would mean that events A and B are dependent. If the probability has not changed because of A, then we would say that A and B are independent events. So conditional probability has this formula. So you can look at it as just using that formula, and that works, or you can think of it as narrowing down the outcomes to only those that satisfy event A. Then within that smaller subset, count how many are also satisfying event B. So you could look at it as the number in A and B in a single trial. So that means the intersection and, or the both and rather than the and then, right? So if they can both happen at the same time, we count how many of those satisfy. And then we divide by only the number of observations in A, or not observations. They're not observations. Observations implies that you've collected data from an experiment that you've already done. In the way we're talking about probability now, we don't know what's going to happen yet. So it would be all the possible simple outcomes in A. So here's an example. Let's calculate the probability of getting a king given that we know it's already a red card that we've drawn. Okay, so in other words, we're going to draw one card. And let's say we show it to somebody and they say it's a red card. And then you're trying to figure out the probability that it's a king. So now that we know it's red, we can use this formula and we can calculate the probability of both a king and a red card happening on the same card, and then divide that by the probability of just getting a red card. So that would look like this. There are two cards here that are both red and also kings out of the entire deck of 52. So that's 2 out of 52. Divided by the probability of getting a red card, which is half of the deck, 26 cards out of the entire 52. So notice what happens when we do this formula. If you remember dividing fractions, you would do keep, change, flip, keep the first fraction, change to multiplication, and flip the second fraction. Well then, because our denominators are the same, they end up canceling out. So we have a reduced version of this, and that's a typo. That should say 4 out of 26 there, and that reduces to 1 out of 13. Is that right? It seems weird. Let me fix that. Okay, so I fixed the typo. It should have read 2 out of 52 times 52 divided by 26. Then the 52s cancel, which leaves us with 2 over 26 here, which reduces to 1 out of 13. So we know the answer is 1 out of 13. That's the probability of drawing a king knowing that it's a red card. Now let's look at it another way. If we narrow it down to only the red cards and act as if these black cards don't even exist, then we have a sample space of 26 instead of a sample space of 52. Now within that, we look for the two cards that are kings, and so we have 2 out of 26, right? The number 2 out of 26 reduces to 113, giving us the same result as before. In the next video, we'll work on the addition rule. See you there.